Okay, time to move. So the topic today is complicated, but it is central to your entire subsequent career as chemists. You will see Fourier transform everywhere. You will see it in NMR spectroscopy, in infrared spectroscopy, in magnetic resonance imaging, in just about every digital filter you ever see that gets rid of your noise and amplifies your signal, in differential equations describing electrical circuits, in electrochemistry when you solve the equations governing diffusion and flow and so on. So a central topic, but before I go into the math, let me put some motivation in place for why you might want such a transformation to exist. So item 1 is motivation. Imagine you are, say, a radio astronomer, and what you detect is the voltage in some giant antenna. So that is your voltage or some other signal, and that is your time. And of course you would like to observe your signal at a few specific frequencies that you are interested in, and say we've got some signal that is recorded and it looks like that. So clearly there is some low frequency present here, and there is some high frequency that is simultaneously present with it. And let's say the high frequency is the hyperfine line of interstellar hydrogen that you are really interested in, and the slow frequency is Taylor Swift on MTV that you are really not interested in. And so what we need to do is to reject one of these frequencies and pass through the other. For that, we need to know what is in there. So a different representation is needed of what is the amplitude of my signal, but not as a function of time, but as a function of frequency. And that signal, if we look at the absolute amplitude, would appear something like this. You would have a component at a low frequency and a component at a high frequency. If we are dealing with nuclear magnetic resonance, we are detecting voltage in our instrument probe coil as a function of time. That voltage comes from the induction that the magnetic field creates in the detection coil, and that would be our NMR spectrum. If we are doing acoustics, this would be pressure reading in some acoustical sensor or a microphone, and these would be the frequencies that are present in the sound. And again, if we are dealing with some kind of acoustic processing, say our singer didn't quite hit the correct note in there, well, we might cheat mathematically and just shift that frequency by a little bit and then transform it back into a time domain representation. This is what routinely happens in digital post-processing of music these days. So clearly it is rather useful to take a signal that came out of the instrument, and that signal would normally be in the time domain, and transform it into an equivalent representation, but the one that has our signal separated by frequency, and we have different amplitudes. Thankfully, such a transformation exists, and it is called a Fourier transform. So item 2 on the agenda is the formal definition. Well, let's think about what that might be. Clearly, we are expanding that signal in the various oscillatory components, which are sines and cosines or complex exponentials, if we put them together using Euler's formula. Then we are expanding this signal as a linear combination of sines and cosines. But of course, the dependence on both the time and the frequency here is continuous. And so we cannot have a discrete sum over discrete frequencies here. So it must be some kind of integral. Now, I will not derive this transformation here. It's a separate couple of lectures. We do it at the mathematics department, but this is a second year undergraduate chemistry module, and so I will not trouble you with the detailed mathematical derivation of this. But f of omega, so the frequency representation of a signal, is 1 over root 2 pi integral from minus infinity to infinity f of t, so the time domain representation of the signal, e minus I omega t dt, the so-called forward Fourier transform. The transform is invertible, and if we would like to reconstruct a time domain signal from its frequency representation, then that is 1 over root 2 pi integral minus infinity to infinity f of omega. So we put the frequency domain representation here, e plus I omega t d omega. You can see they look fairly symmetric. The location of these two pi's can differ because of the different historical conventions in mathematics, physics, and engineering. Sometimes there's nothing in front of this transform and 1 over 2 pi in front of that one. Sometimes there are extra coefficients in the denominator there. So be careful. In the engineering literature you will see a few different conventions. But the one we are using here is the one mathematicians use, the so-called unitary convention that preserves the function norm. So these then are our Fourier transforms, and I will not derive them. Right? I can only simply say that, okay, an integral is a continuous version of a sum, and that does look like an expansion in oscillating functions, with this being the coefficient. Right? So this is as far into the whys and wherefores as we will go in this course. Occasionally, time domain signals do not start at minus infinity. They start, say, at 0, and in that case we have the one-sided Fourier transform. Ft. So f of omega is an integral, but not from minus infinity to infinity, but from 0 to infinity. So f of t e minus I omega t dt. Quite often the case, for example, in chemical kinetics and magnetic resonance, where the signal does begin at 0. Now, let us actually check that this transformation has the properties that we want, that it takes an oscillation in the time domain and it puts a peak in the frequency domain at the frequency of that oscillation. So let us get some typical signal. So it needs to oscillate, and I will also make it decay. So we will consider the following function. F of t will be e I omega t, so the sine and the cosine there. And typically, at least in magnetic resonance and in acoustics, signals decay, and so I will put a decaying exponential on top of that as well. So what that practically looks like is if we plot this f of t as a function of time, the real part of it, then the real part begins as a cos, it oscillates and then also decays, so it's going to be something like this. And that is a fairly typical signal that, for example, you would have in nuclear magnetic resonance when you detect a single line sample in the time domain after you give a pulse. Okay, let us Fourier transform this and see what we get out. So our frequency domain representation, as per the definition, is going to be that. So 1 over root 2 pi integral. We start at 0, and so the Fourier transform is one-sided here. Then we put our function into the integral e I omega t e minus lambda t. Then we have another I omega t here, I omega t with a minus. And to distinguish that omega from that omega, I will put a 0 in here. So that is the frequency of our signal, omega naught. So this pertains to our signal, where the frequency is fixed, and this pertains to the representation of that signal, where the frequency is a variable. Okay, so dt. And that's a pretty standard integral. Let's just merge all of the exponentials into one. So we have 1 over root 2 pi integral from 0 to infinity e I omega naught minus omega. And then this is minus lambda, so plus I lambda t dt. So what I've done is I've added all of the indices of the exponential. I've put I omega and I omega naught under the same bracket. So we've got this, and that has a minus, so we have that. And then plus I times plus I gets us a minus, so minus lambda t is here. Well, we know how to take such integrals, so that is, not forgetting, 1 over root 2 pi, then 1 over the index, so 1 over I omega naught minus omega plus I lambda, and then e I omega minus omega naught plus I lambda, and then t from 0 to infinity. Well, at infinity our signal decays. This is why I made it decay, so that it's well behaved. And at 0 the exponential is equal to 1, so the only thing that this term contributes is the minus sign. Okay, so we have 1 over root 2 pi, and then in the denominator I will split it up into the following. So I will have minus in front, then I omega naught minus omega, and then minus lambda, and that is 1. I will then pull the minus in and swap these around. So 1 over root 2 pi, and then that's a plus, so now we have lambda, and then I will swap those around as well. So that lambda without the I, just the lambda, plus I omega minus omega naught. There we go. That's the form that I wanted. Now, terribly obscure so far, because we have a complex number in the denominator. Let us split this fraction up into the real and the imaginary part and look at the real part. Well, how do we do that with fractions? We multiply the numerator and the denominator by the complex conjugate, so that we have a complete square in the denominator, which has to be real. So that will be lambda minus I omega minus omega naught, and then also divided by the same. And then in the denominator we have a square, and in the numerator we have this 1 over root 2 pi, then lambda minus I omega minus omega naught over lambda squared plus omega minus omega naught squared. And what I will do here is I will for now ignore the imaginary part. You will see a lot of it when you do magnetic resonance. For now we will simply say, okay, let us focus on the real part of that signal. So keep stuff real, and that is 1 over 2 pi, then lambda over lambda squared plus omega minus omega naught squared. All right, let us take a look at this function that we have just obtained. That is our f of omega, the frequency domain representation, hopefully, and that is frequency. Let us think about this. Let us pick up some reasonable decay rate. So lambda is a reasonably small positive number, so that the signal decays slowly. That's our decay envelope here. Then that's a positive number, that's a positive number, fine. If we are very far from the frequency omega naught. So if this is, let's say, far to the left of it, so somewhere here, what happens is this term in the denominator is large, the fraction is consequently small, so our signal starts off small. As we approach our omega naught, this term here becomes close to 0, the square makes it even smaller, and then this lambda is already a small number, so the fraction becomes large. And it becomes the largest when omega is equal to omega naught. So we have a rise. And then as omega starts to depart again from omega naught, this increases and the fraction therefore drops. So that is what we are going to see. And indeed, as you can plainly see, we do have a peak at the frequency omega, and the width of that peak is actually a function of lambda. We will not go through the detailed math here, but the greater the lambda, so the faster this oscillation decays, the broader the peak. So this width is proportional to lambda. And you will see a lot of that when you do nuclear magnetic resonance, where individual nuclei would have different frequencies and therefore different peak positions, and their oscillations will decay slower or faster, and so different lines will have different widths. So yes, as you can see, this transformation does what it says on the tin, and for every oscillatory signal it just puts the peak at the corresponding frequency. And a significantly harder calculation is backwards, because we have something in the denominator there, but if you go through the tedious exercise of plugging that function back into the reverse Fourier transform and taking that integral, you will get that oscillation back out of the inverse transform. Okay, so that seems to work, and that is quite useful. So let us now explore the basic properties. So item 3, properties. Well, firstly, the obvious property of any integral is linearity. So property A, linearity. And what I'll do is introduce a notation for our transform. I will say f of omega is f plus operator acting on f of t. I don't know if you've encountered operator notation yet in quantum mechanics. You eventually will, but there's a function and there's something in front of it, and that is in some general sense an instruction on what is to be done to this function called an operator. And in this case the instruction says take this function and calculate the favorite Fourier transform of it. Then f of t would correspondingly be the f minus f of omega. And here, of course, f of t and f of omega are two different functions, right? So, for example, f of t was this oscillation, and f of omega is this so-called Lorentzian peak. And this is another interesting piece of sloppy notation that we use in physics, right? This is not the same function of a different argument. These are two different functions. One of them is the time representation of the signal, the other is the frequency representation of the signal. So you will see a lot of this when you do quantum theory eventually, probably actually quite soon, because I think Skylaris has you doing Fourier transforms like on Tuesday in the computational chemistry classrooms. Okay, so you will meet operator notation there. Fine. The first thing we will observe as properties go is that if we put a linear combination of two functions under this integral. Of course, the integral of a sum is a sum of integrals. The integral of the function multiplied by a constant, we can take the constant out. And so the Fourier transform of a linear combination is the corresponding linear combination of Fourier transforms. So f plus or minus acting on alpha f of t. Well, let's keep it plus because we specifically indicate that a function of time, but exactly the same linearity applies to the minus. Beta g of t will be alpha f of omega plus beta g of omega. So if we send a combination of signals into the Fourier transform, we receive the corresponding combination of their frequency spectra. Item B, and this is why they are called the forward and the inverse, they undo each other. And formal proof for that does exist, but unfortunately it relies on delta functions, and you haven't had the delta functions in your chemistry module, so I will state this without proof, that both the forward and the backward Fourier transform, if they're done one after the other, return the original function. So f of t is f minus acting on the result of f plus acting on f of t, and f of omega is the result of the f plus undoing the f minus on any other f of omega. So essentially f plus followed by the f minus is what the mathematicians call a unit operator. It's an operation that does nothing, right? They are each other's inverse in the operator algebra sense. Okay. One of the most convenient properties that you will use a lot when solving differential equations, and this is in fact in a lot of cases how differential equations are solved on a computer these days. So these are current active algorithms that we are using. Certainly I'm using them every day. Is a Fourier transform maps differentiation into multiplication, and that's quite a loaded statement. So let's just say ft of a derivative, and let's try to find out what is going to happen if we Fourier transform the derivative of a function. So 1 over root 2 pi integral from 0 to infinity, so we are using physical functions. Here are the ones that begin from 0, and then f prime of t, e minus I omega t dt. Well, what can we do with this? Well, we can obviously just integrate it by parts to get rid of the prime. So our by parts integration will be u equals e minus I omega t. du is minus I omega e minus I omega t dt, so the standard differential. Then our dv will be f prime of t dt, and v is therefore f of t. And then, of course, reminding you what integration by parts is, it's uv from 0 to infinity minus integral from 0 to infinity v du, not forgetting the 1 over root 2 pi in front of all of this. And let's just plug it in. So 1 over root 2 pi, then u is that and f is this, so it's just f of t e minus I omega t from 0 to infinity. Minus in the rule cancels with the minus here, so we get a plus plus I omega, and then integral from 0 to infinity v du, and v is f, and du is I omega, then e minus I omega t dt, and the minus that we had here cancelled with the minus which we have there. Okay, our function is physical. It decays at infinity, so at the upper limit we have a 0, but at the lower limit the exponential is equal to 1, and this is just f of 0, so the initial condition. So what we then have, 1 over root 2 pi, and then minus f of 0. And then look at this, that's just the Fourier transform of the original function. So plus I omega f of omega. So f of omega. And that is it. The one remaining thing is to notice that this is missing our root 2 pi. So what I'll do is that needs to be multiplied by root 2 pi. And finally, when I open all of the brackets, I get I omega f of omega and minus f of 0 over root 2 pi. And that's the final answer. This doesn't look like much until you start thinking about what this means computationally. Imagine we had some horrible differential equation which we would really not want to solve. In the time domain, all the usual horror, right? You chemists, you've seen chemical kinetics. However, in the frequency domain, the only thing we need to do is multiply f of omega by omega. So it's multiplication, it's very simple. So Fourier transform maps complicated equations in the time domain into less complicated equations in the frequency domain. And of course, what we can always do after we've solved it for f of omega is either to reverse the Fourier transform ourselves using that inverse one, or just ask a computer to do it for us. So a lot of the time, particularly in the kind of electronic structure theory calculations that Chris in fact is doing, and this is something he is going to illustrate, one of the fastest ways of differentiating a numerically defined function is to Fourier transform it, multiply it by its own argument, and then Fourier transform it back, and poof, you have a derivative. And you know, for noisy functions, for numerically defined functions, this is a significant advantage, because in particular Fourier transforms are quite efficient and can be efficiently implemented in the currently available hardware. Okay, let us go through an example of this, and we'll just use our dear old radioactive decay as an illustration. So, example. I will use a pretty much trivial differential equation, but no, I will first use the trivial one, and then I will use a significantly more complicated one to illustrate the power of this approach. So starting simple. Some substance just goes somewhere with a rate constant k. We don't particularly care where it goes because the reaction is irreversible, and as you all know, dA by dt is minus ka. First order chemical kinetics. Okay, and we do have the initial condition. We know the concentration or quantity of A at time 0. So say A at 0 was some initial quantity A naught. Let us apply the Fourier transform to both parts of that equation. So we've just proven the derivative property here. So if we have that, so that will be I omega A of omega. So that minus the initial condition divided by root 2 pi. And you can see why engineers had their convention about sticking all of these into the inverse Fourier transform. So if we had no root 2 pi here and 1 over 2 pi there, then there will be none of this messy coefficient here. So, but our convention here compels us to keep this 1 over root 2 pi. And on the other side, minus Ka, this is of time, is minus Ka of omega. What was a differential equation suddenly became an algebraic equation that is easy to solve. So what we do is move that over here and this over to the other side. So we have I omega plus K A of omega equals to A naught over root 2 pi. Just divide both sides by that bracket and we are essentially done. So A of omega is A naught over root 2 pi 1 over I omega plus K. So we have solved the equation in the frequency domain. We can either take that inverse Fourier transform integral now, or we can instruct a computer to do an inverse Fourier transform for us, and that's it. The differential equation has been solved. Well, admittedly, you could say that wasn't too much of an equation. Let us go through something where, you know, a certain amount of sweat would be necessary to solve it, and we will take one that is non-uniform, so it has a source term. So another example is f prime of t equals minus 3f of t plus e to the minus t. So again, first order kinetics, but with a source. Our f decays, the rate constant is 3 in this case, but somebody's standing there with a shovel and adding more substance into the reactor, and they get exponentially bored with that, so eventually they stop doing it. Let us find out what is happening with the solution here. Okay, as you know, if we were to solve this the regular way, we would have to first forget about the source term, solve the equation, keep an indeterminate coefficient, declare it a function, resubstitute into the full equation, solve for the indeterminate coefficient, get another indeterminate coefficient out, determine it from the initial condition. This is good 20 minutes of bored work. Now let's do it with the Fourier transform, and we will declare some initial condition that I don't even mention here, I think. Or we will simply say, okay, f of 0 was equal to 1. Whatever arbitrary units we have there. Fine, let's do the Fourier transform of both. For that, we just use the property we have proven in here. So that would be I omega f of omega minus f naught is 1 over root 2 pi, and that is minus 3f of omega. And the Fourier transform of an exponential we in fact have already obtained. Notice this. If I put omega naught to 0 and I put lambda to 1, that is my final result there, and I had it here. So this is 1 over root 2 pi then we have 1 over lambda is equal to 1 and omega naught is equal to 0. That's it. And once again, you can see that the equation's algebraic, and we can easily solve that for f of omega. So I will take that term and move it to the right-hand side, and I will take this term and move it to the left-hand side. So I omega plus 3 f of omega is equal to 1 over root 2 pi, and then we will have 1 plus I omega, and that term here plus 1. Simplify it somewhat, probably not really necessary, but let's do it. F of omega will be 1 over I omega plus 3 times 1 plus I omega plus 1 over 1 plus I omega. And that's literally it. So you can see a fairly simple function in the frequency domain. And once again, a little bit of exercise with integration. You all did your integrals in your first year. I will not bore you with that, but normally we don't even do that. We either type this into Mathematica and tell it to reverse transform it for us, or this is numerically defined anyway, and so we do the Fourier transform numerically. So as you can see from these two examples, Fourier transform maps potentially nasty differential equations in the time domain, and of course similar properties apply to second, third and higher derivatives, and even to the integrals as well, into relatively simple things in the frequency domain, and this is why it is practically useful. Okay, a few more properties, so we just continue with our properties. So that was C, so now we go D. Derivative of an ft. So not only can we simplify the Fourier transform of a derivative, turns out we can simplify a derivative of a Fourier transform. So let us take some f of omega and differentiate it with respect to omega. Let's see what's going to happen. So 1 over root 2 pi integral minus infinity to infinity, or let's keep it physical, from 0 to infinity. And then we have f of t e minus I omega t dt prime with respect to omega. Well, we are differentiating here with respect to a quantity that the integral only depends on parametrically, so we are not even interfering with the integration process in any way. So for the purposes of that derivative, that's just a constant. The integral doesn't depend on omega because it's the integral with respect to time. F of t doesn't depend on omega, so for our purposes it's a constant. The only thing that does depend on omega is that exponential. So that is going to be then 1 over root 2 pi integral from 0 to infinity f of t, and then the derivative of that with respect to omega minus I t pops out in front, e minus I omega t dt. We will take minus I out in front, so minus I over root 2 pi, then integral 0 to infinity, and then t f of t, e minus I omega t dt. You can see this is still a Fourier transform, but two things have changed. Firstly, minus I is in front, and secondly, it's not a Fourier transform of the function, it's the Fourier transform of t f of t. So that is minus I f plus acting on t f of t. Once again, as you can see, the derivative has disappeared and got replaced by a multiplication in the reciprocal domain. So the same property, differentiation in the time domain maps onto multiplication in the frequency domain, differentiation in the frequency domain maps onto the multiplication in the time domain. So both ways we have a simplification. And the final property, there are many more, but the final property that I will cover in this course will appear a bit obscure at the outset because you have not encountered digital filters yet, and you haven't encountered convolution filters yet. To give you an example, if you are asking Photoshop to blur the image, it has an operation called a Gaussian blur. That's a convolution. Or if you are asking it to sharpen the image, it undoes a convolution that was presumably applied to it. And there are a few more operations like local smoothing filters in a lot of radio spectroscopy, bandpass filters, and so on, which are ultimately expressible as the following operation. So the convolution of two functions, and that will be property E. So convolution. A convolution of a function f with a function g is defined as follows. It's an integral from -infinity to infinity, f of tau g of t minus tau d tau. To give you an example of where this is useful, imagine we have a signal that is very noisy. So we have lots of noise, and there's some peak sticking out of that noise. Depressingly common situation in magnetic resonance, unfortunately, in which I work professionally. Then we would like to get rid of that noise by a local averaging filter. So what we do is we put, say, a Gaussian peak somewhere here, and we say, okay, we take that point and multiply it by this value. We take that point and multiply it by that value, that point by that value, that point by that value, and so on, like this. And then we sum it all together and we divide it by the area of this Gaussian curve, and we put the result as one point of our answer. So you can see what's going to happen, right? We have our noisy function, then we take the local weighted average and we put one point in the answer, then we shift this Gaussian by one click. We take another local weighted average and we put the next point and the next point and the next point. So it stands to reason that what is going to happen as a result is that this signal, so let me use another color for that, will get smoothed because the noise will partially get itself averaged out. So what is going to happen in practice is we will have a signal that looks like that. The peak will be somewhat broadened, but the noise would largely disappear. And so this is f of t, and this smoothing bell, the set of weights, is g of t. And the red line is this convolution. So as you can see, quite useful for denoising. And the Fourier transform has a lovely property. Imagine what we have to do here. For every single point in the answer, we have to take this entire integral from -infinity to infinity. That's a lot of calculations, particularly if your signals, you know, they can be weeks long in some radio spectroscopy. So this is a seriously expensive calculation. Thankfully, Fourier transform tells us that convolution in the time domain maps into multiplication in the frequency domain. So what we need to do is to take the Fourier transform of f of t multiplied by the Fourier transform of g of t and take the inverse Fourier transform of the result. And that is our convolution. And of course, this is significantly easier. Fourier transforms are efficient. Multiplication is trivially simple. Inverse Fourier transform is computationally efficient. And so this is how nearly all convolutions are computed these days. And this is how the digital filters are therefore applied. You take the Fourier images of both the function and the filter, multiply them, and then apply the inverse Fourier transform. So you will not see it until maybe 4th year, but maybe you will see it in some computational practicals. Okay, so applications. That is item 4, I think, on the agenda. I've already mentioned digital filters. If we return to the original picture that I had here, let us say that that's the space aliens and that's Taylor Swift. And depending on your disposition, you would prefer either one or the other, and I would prefer the aliens. And what we can do is, in the frequency domain, we can multiply the aliens by 1, and we can multiply Taylor Swift, sorry Taylor, by 0. What will happen, of course, is that frequency will be obliterated, and then when we do the reverse Fourier transform of the result, so the result will be something like this, and then there's nothing here. When we do the inverse Fourier transform of that, the slow frequency will remain and the fast frequency will be gone from the data. So that is what it's going to look like, and that is called a digital filter. And every time you are posting a video on YouTube and you're doing some pre-processing, there will be a little clicky button there called denoise. And that is what it does. It knows which frequency ranges the typical human voice is, and everything else it considers to be noise. So it goes into the frequency domain, multiplies the voice by 1, everything else by 0, does the inverse Fourier transform, and there we are. In the more advanced packages, there are more interesting options. Says increase the pitch or lower the pitch of the voice. What it would then do is it will take these frequencies and shift them either higher or lower, and then do the inverse Fourier transform, and behold, the pitch of the voice has been increased or lowered. So that is the digital filtering. There are more interesting applications. So here A, so digital filters. So B, JPEG and MPEG. You are too young to remember when JPEG turned up, around about 95, maybe 93 or thereabouts. That was a proper revolution, because in 1993 the computers that we had a few megabytes of memory, and of course 1000 by 1000 image is your 3 megabytes. So what JPEG did is it took the image, it separated it into 2 channels, chromaticity and luminosity. So chroma and luma. Human eye is more sensitive to the brightness of the image than it is to the color, and so that can be compressed less than this, but still you can do that independently to these 2 channels. Then it did Fourier transform, actually discrete cosine transform, to keep the mathematics real, and it built the frequency map of both chromaticity and luminosity, and it only kept the low frequencies. So this is Fourier transform in both dimensions of the image, right? So double integral. And then storage. And storage with additional run length encoding or zip or whatever it is. This reduced the storage requirements from a few megabytes to a few kilobytes, by a factor of, if you want high quality, a factor of 10. If you're okay about the quality, maybe a factor of 100. You have all seen those blocky overcompressed JPEGs on the internet. That's somebody being overly liberal with the Fourier transform. So this is what happens in JPEG. Then the famous MP3s are exactly the same. The image, the sound clip is divided into parts. The parts are Fourier transformed. Certain frequencies that human ear cannot perceive or that human brain automatically reconstructs if they're missing are dropped. The result is contains a lot less information, a lot more compressible, and so 100 megabytes that it took on the DVD, right, becomes just 1 or 2 megabytes that compressed representation would have. And again, if you overdo it, you can hear by your own ears that, okay, that's an overcompressed JPEG because there are clearly frequencies missing and some frequencies are in the wrong place. So this is what it is in practice useful for. Okay. The final thing that I need to mention is the complexity of the Fourier transform calculation. So remember, when the computer does an integral, it actually does it in a discrete representation. So the frequency domain is digitized point by point, and so is the time domain. And if we represent our integral as a discrete sum, it will be a sum over k 0 to infinity f of tk, so discrete representation of the time domain, and then e minus I omega k tk, and then dt becomes delta tk. Let's think about complexity of doing such a calculation. Every single point in the frequency domain requires you to take the sum over the entire time domain and the corresponding number of multiplications. So you need, if you have n points in the function in the time domain, you need n multiplications per 1 point of the answer. But if you have n points in the answer, which you must have in order not to lose any information, you need another n. So the complexity of a naive Fourier transform is order n squared, where n is the number of points in the sample. And if you have your MPEG compressed audio clip, it can have billions of samples in it, so roughly 10 to the 6 to 10 to the 9s. Having to do 10 to the 12s to 10 to the 18s multiplications is a bit difficult. Thankfully, in '83, an algorithm was found that does it in n log n. So log 2n operations, which is roughly, very roughly, because log drops quite quickly, proportional to the number of samples that you have in your signal. And so that was 1983. And this is where the digital signal processing revolution has started, because suddenly all of these operations, instead of being astronomically expensive, actually became computationally affordable. And then computers turned up that are really powerful. And so now all of this is routine, even in your mobile phone. Okay, the summary of the lecture. There's this lovely transform called Fourier transform, which takes the time domain representation of your signal and produces the frequency domain representation. Apart from the obvious advantages associated with such an operation, it also maps differential equations in the time domain into algebraic equations in the frequency domain, which is the principal area in which it is used. It is used a lot in digital signal processing and filtering, and you now understand exactly why JPEGs look so horrible and MP3s sound so bad. That's because somebody has overdone the Fourier transform, frequency elimination. They've dropped far too much. Any questions?